Okay, Nick, do you think we should get started? Okay, terrific. All right, and just to verify my slides showing. Yes, okay, thank you. Welcome, everyone. I apologize for the delays in getting started. We have an unusual experience where a number of our speakers are together in a meeting room at PNNL, and we've had to do some juggling to get all of the technologies to work for us. So thank you for your patience, and thank you for joining us today. My name's Karen Smith, and I'm an advisor at Pacific Northwest National Laboratory, and I'm one of the deputy directors of RemPlex, which is the Center for the Remediation of Complex Sites. And I'd like to introduce two of my PNNL colleagues, Nick Chofuku, who is another RemPlex deputy director, and Fred DeLewis, who is a chief geophysicist at PNNL, and he'll be moderating our seminar today. And I'd also like to acknowledge our PNNL colleagues, Kelly McIntosh, Heather Brickey, and Melissa Perdue. They've been helping us organize and promote the seminar. As I said, this seminar is brought to you by RemPlex, and RemPlex is a forum that we established to share knowledge and promote collaboration in the realm of environmental remediation. We periodically run seminars and other types of events, and we maintain a catalog of information from all of our events on our website. I'll share the link with you in just a minute. And if you're interested in learning more about RemPlex or about our previous seminars and other events, you'll be able to get to that content from the RemPlex website. Now, turning to today's seminar, before I turn this over to you, Fred, there are just a few logistical details to cover. We are recording the seminar, and we will make the recording available on the RemPlex website following the seminar, along with a copy of the slides that are presented today. We're going to take a few questions at the end of each presentation, but our plan is to reserve a chunk of time at the end of the seminar that will be for open discussion. I'd like to ask that you please mute your microphones during the presentations. Thank you very much, Fred. I'm going to turn it over to you.
Great, thank you, Karen. Today we have a workshop or seminar entitled Optimizing Remediation Outcomes Through Integration of Geologic and Geophysical Data. The most challenging element of any remediation project, particularly those with groundwater contamination, is the uncertainty and potential heterogeneity of subsurface conditions. Subsurface heterogeneity has confounded the progress, delayed remediation goals, and caused budget overruns for many groundwater restoration efforts. Conceptual site models need to provide reasonably accurate and complete representation of the subsurface in order to successfully guide groundwater remediation activities. This seminar will discuss best practices for integrating geologic and geophysical data to enhance CSMs and optimize remediation outcomes. We actually have two sets of speakers today, two presentations. The first is Remediation Geology and Applications of Environmental Sequence Stratigraphy, that's ESS, to optimize groundwater remediation outcomes. And our first speakers are Rick Cramer and Mike Shultz of Burns McDonnell. I'll give you a little bit of background about Rick and Mike and then turn it over to them. Rick has over 30 years of experience as a consultant in water or environmental industry, focusing on applying advanced geologic methods to improve conceptual site models to optimize remediation outcomes. Rick developed and introduced the practice of ESS to environmental industry in 1994, culminating with the 2017 EPA groundwater technical issue paper on the topic. He started with Burns McDonnell in 2016 and built their ESS practice. He began his career in the petroleum industry and earned his BS in geology at University of Pacific Stockton and his MS in geology at the University of California, Davis. Mike Shultz is a geologist and sequence stratigraphy specialist with over 25 years of multidisciplinary experience in subsurface investigations. His career has spanned both oil and gas exploration and production, as well as environmental assessment and groundwater remediation. Mike is a groundwater remediation industry thought leader, co-developer of ESS, and the lead author of the 2017 EPA groundwater technical issue paper on the topic. Mike earned his BS in geology at Purdue and PhD in geology at Stanford. So at this point, I'd like to turn it over to Rick and Mike for the first presentation today.
Thank you, Fred. Share my screen. Let's go. There we go. Okay. Thank you all for attending. I'm sorry. It is. Yeah. I think it's on. You good? Okay. Here, we'll get started. All right. Thank you. So environmental sequence stratigraphy, or ESS, has been established as a best practice for groundwater remediation practices by the US EPA, Air Force, and Navy. And today we hope to show why this geology-focused approach to targeting groundwater remediation should also be considered a best practice in the DOE space. So I'll give a quick outline of what we are going to present. I'll start off by first talking about what remediation geology and environmental sequence stratigraphy are, and then also why they're critical to groundwater remediation projects, and then hand off to Mike, who's going to get into more details about the technology and present a couple case studies. So I started my career in the 80s in the petroleum industry, and in that industry, like with groundwater, there's a focus and importance on understanding the subsurface and stratigraphic controls on fluid movement, fluid migration, fluid flow. And geology, robust geologic models are the standard in that industry, and were developed, and billions of dollars have been spent over decades in developing the understanding of stratigraphy and the science of sequence stratigraphy. That was developed in the petroleum industry to address the economic challenges of producing fluids in the subsurface. So that's where the basis of this technology, environmental sequence stratigraphy, came from. And that became the standard in geology and academia for understanding stratigraphic sedimentary basins and stratigraphy, the science of stratigraphy in general. Now, with environmental sequence stratigraphy, it's basically taking the concepts of depositional systems and facies models and applying it to the kind of data sets that we collect in the groundwater world, and specifically in environmental consulting. And so what I show here are the three basic steps of environmental sequence stratigraphy. And really, these are the same steps that you would put together for any geologic model of the subsurface. The first one is doing research of the regional geology, understanding depositional systems and associated facies models in order to get an idea of what the subsurface includes under your project. The second is about your existing data and leveraging that existing data to where it can be interpreted based on the genetic relationships of the lithology. So what I mean by that, and Mike will show this in more detail, is developing vertical grain size, formatting the data that emphasize vertical grain size patterns, because these relate to depositional systems and the facies models that the subsurface was created by, okay, that are responsible for the development of that. So that's a key distinction here, is bringing in the understanding of regional geology and depositional systems into existing lithology data. And then that's for the final reason, and that's the capability of being able to interpret and map between your data points and map out the subsurface permeability architecture, which is guided by the geology and geologic features. Because the bottom line is that the geology really forms the primary control on groundwater flow and also migration of contaminants in the subsurface. The geology is really like the subsurface plumbing. And this is what I've spent most of the last 30 years of my career, is focusing on this application of improved and more robust geologic models to groundwater remediation conceptual site models. And this culminated in 2017 with the US EPA best practice paper that was co-authored by by Mike and along with Colin Plank and myself at Burns McDonnell, as well as Ken Eman with Chevron now, and also Herb Levine, formerly at EPA Region 9. So just to give a review of where this fits in the components of a typical groundwater contaminated site, site conceptual model, is the geology is really your base level and your foundation. I mean, we have our other data sets, our groundwater hydrogeologic data, primarily groundwater elevation data, as well as chemistry data. Well, those data sets are very dynamic. They change a lot with changing conditions, okay? Now, not so with the geology. The geology is static, and that's really the framework that we really need to understand first. So then we have that within which to start to evaluate those other more dynamic data sets. And then it becomes an iterative process, which one ends up informing the other as we move along in understanding the details of the subsurface. And this was a point that was made in a 2013 2013 publication by National Research Council that found that it's geologic heterogeneity that has prominent influence on the challenges of complex contaminated sites. So that's why this focus on a better understanding of the geology. Now, I showed the components of environmental sequence stratigraphy and referenced the EPA paper, which is a good guidance document, but really probably the most important component of this approach and this technology is the expertise of the practitioner, okay? Because when you become a geologist and you get your bachelor's degree, you get exposed to over a dozen different subdisciplines, as I show here. What is important is having the expertise and your career dedicated to understanding stratigraphy, sedimentology, in order to be able to practice and be able to have the understanding that's needed for doing pattern recognition. I mean, stratigraphers spend their career just looking at outcrops and trying to understand all these different depositional systems and facies models. And Mike will show you that in his presentation. And the medical model I like to relate it to is like a radiologist. You want a radiologist to review and analyze your X-ray or CT scans, right? Not a podiatrist or a general practitioner. Well, you know, same thing with defining your stratigraphic framework. It's really, really important to have that expert practitioner. Now, a couple other reasons, you know, the why this is important. I mentioned about Department of Defense endorsing this approach. Well, they had been applying ESS as a standard since about or starting at about 2010. And then a year ago, they did an evaluation of their remediation projects overall to identify different components that are important to remediation optimization. And what clearly came on top of everything was the conceptual site model. That is the most critical component of a groundwater project in order to optimize your remediation. And then that same year, they did an evaluation of, it was enterprise-wide, of their ESS projects. And, you know, to date, they have contracted over 80 different facilities throughout the US applying environmental sequence stratigraphy. It's also their standard approach for PFAS remedial investigations. And you know, what their lead remediation engineer found was that, you know, oversimplified CSMs just result in an over-engineered remedy, which also results in higher costs. And lastly, just as this example, what actually leverage this better understanding of the subsurface at Kirtland Air Force Base, where several years ago, there were just issues with all the stakeholders being at odds. And what they did is they brought in this improved understanding of the geology that gave answers and better predictions to what's happening with the subsurface than just looking at groundwater data alone. And they did this by taking the public and stakeholders out on field trips, showing them where the subsurface cropped out, what it looked like, presenting posters. And this resulted in turning around again, both the public and regulators, because it's about reducing the uncertainty of the subsurface and having a better definition of where contaminants are potentially migrating. And it resulted in a letter of commendation from the Assistant Secretary of the Air Force. And so just with that overview and background, now I'm going to hand off to Mike, and he's going to talk more details about the technology.
Oh, thanks, Rick. Thank you, Fred. We good? Okay. Yeah. So as Rick said, it's dark down there. We're talking about something that we can't see. As much as 90% or more of groundwater flux flows through 10% of less of the cross-sectional area. Aquifers are almost always dominated by preferential flow pathways. And the part that's not the preferential flow pathway, that's a place for contamination to be stored and re-released over decades or hundreds of years. So what we're hyper-focused on is parsing out to the best degree possible where those preferential flow zones are, conceptually where that flow is occurring. And I show this this picture here from a 1980s petroleum industry course manual on sequence stratigraphy. And what it says is, got more work than you can handle. Sequence stratigraphy can lighten your load. And that's how it was developed, as a predictive framework, because we will never know exactly how every sand or clay bed correlates from one well to another. But with sequence stratigraphy and facies models, we can conceptually understand how fluids move through the subsurface and frame our expectations about our needs for resolution, our ability to characterize, and our ability to successfully remediate. And in the age of PFAS, this is of critical importance. And so what I'll do is I'll give a little more background and talk about facies models. And then I will go through a couple of case studies of modest sized sites, I would say. But the point being that this is a scalable technology, from literally individual channels up to basin scale. And we'll talk a little bit about that. So with that, I want to just highlight what I see as the problem of aquifer heterogeneity. And outcrops are critically important for understanding how sedimentary systems shift about through time and deposit their sediments into strata. And the red circle there, that's a person. You can't see that person, but that's to give a sense of scale. So what we're looking at here is an outcrop, sort of a badlands kind of topography. In Alberta, this is the Horseshoe Canyon Formation. So this is more or less at a site remediation scale. And what you have are the white beds in there, the white layers, those are sands, and the black or brown layers are or clays. And so the beauty of this formation, the outcrops that we see here, is that you can literally walk around up the canyons and you can get a sense of the three-dimensional architecture of this hypothetical aquifer. And so the point being here is that, and here's a little zoomed in view, but if this is your aquifer, you have these red lines that highlight the clay units. And these rocks were not deposited from the bottom up, rather they were deposited from left to right sequentially as the channel, in this case, moved through time from left to right. So this sort of shingled architecture or laterally offset architecture is a very common feature in sedimentary systems, and quite often can confound characterization or remedy approaches. And to illustrate that, if we consider that to be a hypothetical water table, and you start drilling wells, and you drill down and you find a sand, well, that must be the A sand, right? And that's the A1. And then so you go over your next location and you drill and you find a sand and it looks the same, so it must be the same sand. But in reality, oftentimes those are disconnected, and instead of correlating, like as shown in the top here, that first sand across and the second and the third, well, in reality, it's more like a scenario shown in the bottom where your barriers to flow, you have these barriers between the shingles, if you will, and groundwater flow would be driven down. And what's more perhaps important is that the anisotropy introduced by this setup here, where your groundwater flow into and out of the page is much more pronounced than left to right. And that's the kind of anisotropy that is so common in aquifer systems and poses real risks for accurate monitoring and delineation and ultimately remediation. So how do we how do we predict that? And this is, I think most people will recognize, this is the Mona Lisa just from a few small pieces. We never have the full picture of the subsurface, but if you have seen this 1,000 times in your life and your brain is already conditioned to know how to fill in the gaps, then that's what your brain can do with just a few pieces. And that's the whole concept of facies models and sequence stratigraphy, is that with just a few pieces we can really frame our expectations for how those wells are connected or not connected in the subsurface. And so this is a block diagram. This shows a number of different depositional environments on the face of the earth, where you have glacial environments in mountains, where those streams empty into a flat area. You have alluvial fans, and then you have a variety of river type systems, and then shoreline systems as well. And the key here is that each of these environments has sort of a characteristic signature that kind of like Mona Lisa's smile, in that if you see in grain size trends, for instance, a finding upward trend, then you have a real hint just from one well that you're dealing with some form of channel system, and that then your expectation is that I will not have laterally continuous sheets, but instead my aquifer may be dominated by these sort of shingled type disconnected deposits. And taking that a step further, this diagram is a similar diagram on the upper right and shows different environments. But even within a depositional environment like B here, in a fluvial environment, you can not only have finding upward type signatures, but also blocky type signatures or serrate signatures, depending on where you are within that environment. So the point being is that within individual environments, you also have sub-environments which have different fluid flow characteristics as well. And then so let's look at, for instance, a barrier island setting here in Panhandle, Florida, for instance. And in this barrier island environment, well, those are complicated too. And those are present not only in modern coastal environments, but also in ancient For instance, the Utah formation of Mississippi, Alabama, that's composed of these types of barrier island systems. And we've seen time and time again how that influences groundwater flow. But this diagram then shows how a series of islands move through time, step back when sea level rises, move back through again. And this shows all of the different types of sub-environments that can be found. So this is a facies model or a depositional model. And what this is a sort of a distillation of our understanding of how sediments accumulate and are preserved in the stratigraphic record in these different depositional sub-environments. So we take information from the surface, imagery, satellite images, drilling and coring operations, remote sensing, historical observations of how, for instance, when a hurricane comes through, what happens to these, and theoretical computer models. And then also really important are these ancient systems, outcrop systems, where we can firsthand observe the stacking of the different aquifer and aquitard units. And then many, many decades of oil and gas field development. These are fantastic reservoirs for oil and gas. And so they've been very, very well studied. And as Rick said, what ESS does is applies those decades of learnings and of distillation of understanding to make predictions away from the wellbore. And so with that, I'll jump into the first case study, which is in the San Francisco Bay Area, the Silicon Valley. It's a former semiconductor and other electronics manufacturing. This is a classic complex site, commingled plumes. It's a Superfund site, and there have been dozens of remedial actions, including removals, injections, in situ actions, and active ongoing pump and treat operations. It's about a mile-long plume, and you will note right away the shape of the plume, which right off will tip us off that there is a degree of subsurface heterogeneity, in addition to pumping influences, of course, that serve to move contaminants in a homogeneous in a sandbox with a unidirectional groundwater flow vector. You would get a very long, linear, very thin plume, and that's certainly not the case here. So let's look at what the subsurface looks like here. So what prompted this work was that a 5-year review identified a well with increasing concentrations, and that pointed back to a source area that was identified by inspection of a potentiometric surface map. And it was indicated that source area remediation should occur as a result of that. However, it's an occupied retail and office space, so that's not entirely feasible or desirable anyway. So we took a hard look at this and tore apart the subsurface to determine what we could about the origin of those increasing concentrations in this well. The historical conceptual site model for the site has many fairly layer cake with the beloved confining layer. However, that did not turn out to be the case once we started to look closely at the existing site data. And what we saw here, and on the right highlighted, is one of the individual boring logs. And so we see very sharp contacts with underlying silt and clay facies, and then we see a very clear trend. And here They describe gravels up to 1 inch in diameter sitting right on the base, very common for a channel type feature. And then a progressive fining in the diameter of the gravel, and also replacing the very coarse sands with silty sands vertically, and then into a silt and into a clay. So this is like the hallmark of a meandering type channel deposit. And so that's how then begin to envision the subsurface, apply the facies models for that type of environment, and frame our expectations for, we're going to have very channelized groundwater flow here. Again, 90% of the flux going through 10% or less of the subsurface cross-sectional areas. And so this is kind of how we made the sausage here in this case, is to begin to use all of the lithology data from the wells to construct surface maps, that is, maps of the materials at different elevations. This map here being for this particular depth zone right here. And what you'll see are there's some sand fairways separated by some swaths of fine-grained overbank deposits. And then the bottom line was, then it became clear that there were on site here in the red box, there were 2 distinct channel orientations, one of which connected to the former on-site source area, and the other of which ran through just the corner of the site and happened to intersect that well in question, which is 9B here, and the screen of that well intersects both of those channels. And then, so we have a channel tapping another source off-site. So what other lines of evidence can we bring to bear on that to validate that conceptual site model? And so what we then turned to was the contaminant fingerprinting, if you will, and looked at the relative concentrations of different constituents. And so with the offsite channel, this channel right here shown in the map view here, what we see is Freon, Cis, and TCE, and very little PCE or vinyl chloride. And as it turned out, that there had been vinyl chloride that was a daughter or a product of degradation from source area remediation in the on-site area. And what you see is in those wells that are in the on-site channel is you have an abundance of vinyl chloride in every one of those wells that's screened within that channel. However, the well in question, that was the reason that we initiated this work, where the 5-year review had suggested increasing concentrations. Well, that well has the whole mixture of all of the contaminants, because due to the fact that it is screened across different channels with different source areas. So simply mapping these channels, and we're talking about channels that are 3 feet thick, but are moving the contaminants and the groundwater through the whole aquifer system. So this resolved a need for additional source area remediation, and was clear evidence of offsite of commingling of this plume. The second case study, so that first case study was an example of application of facies models. That is the conceptual construct of how depositional environments, in that case channels, have an expected distribution and architecture, and how we were able to use that model to condition mapping of those channels with an expectation of widths being relatively modest, channel width, due to the relatively thin nature of the channel deposits themselves. The second case study is from, we published this this paper this past year on Eglin Air Force Base in Florida. This is a study of how we were able to optimize a pump and treat PCE system for groundwater plume. This was a performance-based contract that was not meeting its PBR objectives. And this is an example of where actual sequence stratigraphy, which is more related to changes in relative sea level, was leveraged in order to change the subsurface conceptual site model, move an extraction well without changing any of the capacity. So the throughput of the system stayed the same. The well that was added was 5D, and it wholesale changed the trajectory of the project, and within a number of years, the plume essentially collapsed, and we're able to meet the performance-based objectives. So this is a complicated slide, but this is sequence stratigraphy. And so what happens is that when there are polar ice caps, as we're showing here in this globe of the Earth, well, seawater is stored in the ice caps and sea level falls dramatically. And when that happens, large valleys are cut. Think all over the eastern seaboard, the big flooded Potomac, you know, there's dozens of them. I'm sure you maybe boated on them, but these valleys were carved. And then this block diagram at the bottom left illustrates what that might have looked like during a low stand. However, then when sea level begins to rise again, those valleys are then filled with coarse grained sediment. Those are called incised valleys. And then eventually those valleys are completely filled, and the sea will flood back in, leaving a maximum flooding surface. So what we observed at Eglin was we observed these high gamma ray peaks in geophysical logs, and those are signatures of these flooding surfaces where the sea actually sea level was high and deposited a thin drape of clay across the landscape. And the historical conceptual site model basically considered the site a sandbox, and drew a dashed line connecting those. However, but what was apparent was that clay unit had been eroded in many places, and that in those areas, those were incised valleys that resulted from that fall in sea level, erosion and valley carving, and then backfilling. And those valleys get backfilled with much coarser material, much more highly permeable strata. So when saturated as an aquifer, become a preferential pathway. So this revised interpretation, we then realized that there were no extraction wells within those incised valleys. They were all outside of the incised valleys. And so simply moving a well and installing a well within that incised valley, without changing any of the capacity or throughput of water in the groundwater extraction and treatment system, it dramatically improved the rate of recovery of PCE. And so these represent kind of before and then soon after installation of that well, the collapsing of the PCE plume. So some takeaways here is there is no such thing as a sandbox when it comes to remediation. And in the stratigraphy, what's missing, that is this high gamma clay unit in many of the wells, is often as important or even more important than what is actually present in terms of interpreting the groundwater flow system in a site. And this is another look at that performance curve. This being the predicted curve based on the performance prior to the installation of that one single well in this site. And you can see how that it dramatically improved the time frame, the mass removal rate, and the predicted time frame of actually being able to cease the pump and treat remediation system.
So, all right, Mike, we'll just wrap it up with the takeaways.
Yeah, I can hand back over to Rick. Do you?
Yeah.
Thanks for your time, and I will now hand this back over to Rick. Thanks.
Takeaways are, we can't overemphasize the importance of the practitioner, because just so you know, ESS, it's not a software, it's not a data collection tool, it's about interpretation of existing data. And again, the importance of the practitioner, and it's applicable to, there's a blank there, it's applicable to all contaminants, because it's about understanding the subsurface plumbing and how contaminants move through the subsurface. And lastly, we believe that DOE can reduce the risk of uncertainty at radioactive waste sites and increase environmental and worker safety by having a more focused understanding of their remediation program. Thank you.
Great, thanks, Rick. Thanks, Mike. I think we have time for one quick question. I did see one pop up in the chat, and that question related to using an approach like this and how, let's see, the theoretical framework in terms of the hierarchical modeling and sequence stratigraphy has evolved immensely over the past 45 years. How important is it to stay up to date with the latest models and interpretations?
This is focused on applying conceptual models, and while we and certainly theoretical and numerical models have made great advances in sequence stratigraphy, we are focused on applying conceptual constructs like bases models and depositional models in order to make predictions. And certainly a lot of our work evolves into static and dynamic groundwater modeling and simulations. So that hopefully that answers your question.
Thanks, Mike. All right, I think at this point we should move on to the next presentation. In the first presentation, we heard about how principles from sedimentary geology can help to fill in the gaps between where there's data available at boreholes. This next presentation will take a different tack, perhaps complementary to the same problem, using geophysical information to help fill in the gaps. Of course, these two approaches can be used together, and that's one of the reasons why we brought the two sets of speakers together today in this seminar. So the title of our next presentation is The Use of Geophysics for Refinement of Subsurface Stratigraphic Structure in Support of Geologic Framework Model Development. Our speaker is Judy Robinson from Pacific Northwest National Laboratory. Judy is a computational scientist with field and numerical modeling experience in geophysical methods. She's been with PNNL since 2018, and her work focuses on joint inversion using flow and transport models along with electrical resistivity imaging to determine the feasibility of field electrical imaging. She has expertise in analyzing complex resistivity data, and she earned her BS in civil engineering at New Jersey Institute of Technology, her MS at Johns Hopkins University, and her PhD at Rutgers University, Newark. Judy?
Thanks, Fred. Can you see my slides okay? Does that look okay?
You can.
Okay. Thank you so much for your time. That was a great presentation, Rick and Mark. I really, Mike, sorry, I really enjoyed it. We're going to switch gears now and really focus on using geophysical data and integration of geological and geophysical data to enhance conceptual site models. First, I'd like to acknowledge my co-authors, James St. Clair. He's done all of the seismic work I'm going to present here. John Tomley, who's the field engineer. Chris and Delphine, who's worked on Socrates, which I'm going to introduce at the end. And Rob Mackley, who's the project manager of the Deep Vadosome project, which supported the work that I'm going to present today. The slides are not advancing. Oh, there it is. So we've seen different sites sort of around the country where sequence stratigraphy has helped meet remediation goals, but this talk focuses on the Hanford site. So for those of you unfamiliar with the Hanford site, it's located in southern Washington state, which is over on the West Coast, and it's where plutonium was produced as part of the Manhattan Project during World War II. Plutonium production continued through the Cold War until 1989, and now the site's mission since the early 1990s is focused on cleanup. So a lot of the plutonium activities happen within the center of the site called the Central Plateau, and so this is where we focused a lot of our geophysical investigations. I also want to point out that surrounding the site is the Columbia River, and it's had a big impact on the geology of the site. So I'm going to talk about that in just a bit. So the outline for my talk is, first I'm going to talk about the Hanford Geoframework Model, or the GFM. This is really the backbone of the CSM for the Hanford site. Next, I'm going to talk about geophysical methods, theory, data collection, information extracted, and I'm going to focus on seismic and electrical resistivity tomography. Then I'm going to talk about field examples within the high hydraulic conductivity zone, or the HCZ, and I'm going to introduce what that is. And finally, I'm going to talk about ERT visualization within Socrates, and then finally some conclusions. Sorry about that. There seems to be a big delay. Okay, so Hanford site stratigraphy, it's an interpretation of borehole data and observations. So over on the right is a log showing lithology, and that can be a compilation of core samples, borehole sampling and logs, hydraulic testing. And this is really represented within flow and transport simulations as hydrostratigraphic units. So sort of generalized units are defined for use within the flow and transport simulations. And it is, this actually defines the Geoframework Model, or the GFM. So the GFM is the spatial arrangement of major hydrostratigraphic units. It forms the fundamental basis for decisions on the Hanford site, such as siting wells, contaminant transport, and distribution of contaminants. So this is what's used within the flow and transport models, which is that static data that Mike and that Rick actually introduced. But we need to interpolate between these well locations. New wells are costly, and in all reality, no matter how many wells you drill, there's still going to be site heterogeneity that you can't define just by looking at boreholes alone. So how can we see in between these wells? We've used geophysical methods to do that. We've used seismic and electrical resistivity tomography. So seismic methods utilize elastic wave fields to probe the subsurface. The measurement is the travel time of acoustic energy from a source location called a shot point to motion sensors called geophones. So seismic waves propagate through the subsurface at different speeds, and they reflect and refract at different subsurface boundaries. So refractive waves provide information about lithology, porosity, and saturation. Reflected waves provide information about the location of subsurface boundaries, and surface waves, such as Rayleigh waves, provide information about lithology and porosity, but are insensitive to saturation. Electrical resistivity tomography is a frequently employed geophysical technique because it's sensitive to porosity, moisture content, temperature, grain size sorting, pore fluid conductivity. And the measurement is the injection of a current between 2 electrodes, and then the measurement of potential between another 2 electrodes. And you end up with distributions of bulk electrical resistivity. What I'm going to present in this presentation is bulk electrical conductivity, which is its inverse, because it has some analogies to what hydrologists use, which is hydraulic conductivity. So these geophysical methods are likely to see large contrasts in geological properties, but thinner layers or smaller textural contrasts will likely not be resolved. And as you might have noticed, ERT and seismic methods have sensitivity to overlapping physical properties, but the physics and resolution used to acquire them are different. And so they can provide additional information, and they can provide multiple lines of evidence of stratigraphic structure, which is what we are looking at here. But they're not a substitute for direct borehole information, and that should be used wherever is possible. You'll see in what the work I'm going to show today, we actually have very limited borehole coverage, and the geophysics is providing sort of a first-line evidence of stratigraphic structure. Just a little bit more detail about the ERT data collection. So the depth of investigation is controlled by the electrode spacing. So we use both large and small electrode spacings to provide higher resolution of both deep and shallow features. And we also use different electrode configurations to improve resolution. So as your electrode spacing gets larger, you get a deeper depth of investigation, but you get lower resolution of features. And the opposite is true, where as they're closer together, you get higher resolution of features, but a lower depth of investigation. Seismic data collected in the field can be processed as independent phases. So what I'm showing here is a seismic trace shot gather. So the gather shows all of the data collected from one shot, which is one source location, which is at that offset 0. That red line represents the data shown over on the left, which is the travel time at one geophone location. And from this, you can interpret different phases, and I'm showing 3 different phases. So the refractions are shown, which are the first arrivals, which can then be inverted for compressional wave velocity. The green is showing the reflections, and then the red area are where you have surface waves, which can then be inverted for shear wave velocity. So in seismic data, the depth of investigation is controlled by the offset. So we always use shorter and longer offsets for shallow and deeper resolution of features. So here we are back on the Hanford site, and we started out doing synthetic investigations and then progressed to field studies. We focused on this central plateau area in between the 200 west and 200 east areas, and south and southeast of 200 east, because there's some interest in finding out how contaminants are migrating off of the central plateau and how long it will take those contaminants to get to the downstream receptors, which is the Columbia River, which you can see surrounding the site. So I want to introduce some plume maps to demonstrate why we collected geophysical data in the places that we did, and also the HCZ, which stands for the high hydraulic conductivity zone. So the plumes that I'm showing are the iodine 129 and nitrate plumes. And you can see that we have some migration of the plumes over from 200 west to 200 east. And then the iodine plume appears to be migrating in a southwesterly direction, which is right within the HCZ analysis area. So the HCZ analysis area is where ancestral floods deposited gravel deposits. And you can see so these deposits incise their way into the lower units, and they actually can control groundwater flow and groundwater movement, contaminant movement off of the central plateau. So it's really important to know where these are located. You can see, looking at the map, that the delineation of the HCZ analysis area is very large. There's a lot of uncertainty where it's located. So we conducted our geophysical investigations within the HCZ analysis area, and then also between 200 West and 200 East. The orange lines represent where we did electrical resistivity tomography. These are all going to be static characterization images. Seismic data was collected where the green lines are located. We also tried to collect time domain electromagnetics. It didn't work particularly well on this site because what I forgot to mention is that there's a very deep vadose zone. In some places, it can be as deep as 100 meters or 120 meters. And time domain electromagnetics is sensitive to conductive targets, so that was actually very deep, and our signal noise ratios were very low. So I don't have time to go through everything, but I'm going to take you through to 3 areas. So the first area is area 1. And in this area, we had pretty good control on the GFM. So there was more certainty and more borehole control within this area. So on the left side, you see the colored, on the left side, you can see the colored diagram showing the geologic framework model. And then the bulk electrical conductivity from ERT data is shown on the right-hand side and on the top. You can see that the dip and the location of where one main electrical contrast is at the boundary where those top units, the HF, the Hanford, and the Cold Creek unit, are on top of those Ringgold units, which is designated as RTF, RWIE, and RLM. Interestingly, we crossed a road, so we didn't want to lose resolution at that road crossing, which is why we collected this A1P profile. And you can see even within the shallow area, we see some variations within that blue color, which might be designating differences in textural contrast or potentially moisture content. So James went out and collected co-located seismic. And what you see on the top image is compressional wave velocities, which are inverted from his first arrival pics. You can see that it's designated mostly one seismic velocity contrast up top. The ERT contours are shown there, and they match pretty well where those contrasts are occurring. And then if you look at the shear wave velocity, which is just below that, and then compare that to the ERT, which is below that, where that circles are, it's showing some contrasts in the shallow area, which is actually not designated within the geologic framework model. So using this as a frame of reference, we then went to an area where we had much less borehole coverage, and this is between the 200 areas, where there is a suspected sort of transmissive unit or transmissive zone or paleochannel between this area. So this is a really large area, so we collected profiles of ERT data, and we position each subsequent line based on looking at the previous line. In this area, again, there's few wells, so this is really providing the first line evidence of stratigraphic structure. We took all that ERT data and did a quasi 3D inversion. And over on the right is showing 2 sections. And if you look at where the boreholes, we had a couple boreholes, which are shown there. The bottom of that unit where that high conductivity, the red colors are, corresponded to where the basalt is. And we picked one value of bulk electrical conductivity. This is purely subjective, and we could have chosen a different value, but the idea was to sort of pull out some sort of structure between the 200 areas, some sort of electrical structure. And that's what's shown over on the left, which is an elevation map, which is showing the elevation where the bulk electrical conductivity is, that value shown there. And what you see is this northwest to southeast low elevation, or this dipping low bulk electrical conductivity feature, and it's flanked by higher electrical conductivity areas. This is really interesting because it's hypothesized that the migration is from west to east, and yet this structure is showing more in a south easterly direction. So the scale of this is pretty massive on the kilometer scale, and it would take a lot of time, money, and energy to put enough boreholes in this area. So geophysics has helped provide a first-line evidence of stratigraphic structure. However, we need a better understanding of electrical properties versus hydraulic properties for a more robust interpretation of what we're seeing here. James and crew collected seismic data in this area along lines 3 and 4, which is why I showed lines 3 and 4 along the ERT. This is really interesting. You can see that the lower, so what you're seeing is the gray scale, which is showing reflections, and overlaying on top of that is the compressional wave velocities. You can see that the color scale lines up pretty well with where those reflectors are occurring. And particularly, it's more evident to see in line 4, you can see that you have lower velocities right up against higher velocities at depth, and there's a very strong reflector there. This could be indicative of where a transmissive unit is, where those coarser sediments incised below deeper to create this sort of channelized feature. We are still sort of analyzing this data. James is working on analyzing, and a new borehole is actually between line 4 and 5. So we're still looking this over, but this is really encouraging. The ERT and the seismic data seem to agree, at least in terms of where a hypothetical paleochannel might be located. Finally, I want to take you to area 3. This is really interesting, and I'm going to present the seismic data first because we have a vertical seismic profile within a well here. And this is really powerful data because there were borehole stratigraphic interpretations also within this well. And this allowed for an interpretation of stratigraphy with seismic velocities. So James has, again, this data was collected in 2008, and he reprocessed it. So the grayscale image, again, is the reflections. The color scale is the compressional wave velocities from his first arrival pics. And then he's overlaying the borehole stratigraphic interpretations for the different units. So you can clearly see that the reds are where the Hanford Formation is located. The blue is indicative, and those higher velocities are where the basalt is located. And then those in-between colors can represent the Ringgold units. Interpreting, it's interesting, you can see that the basalt is thinning as we move further south. And this gives us the basis to interpret in areas where we don't have good borehole coverage, which is actually south of 200 East. So here's everything together in a fence diagram showing all the lines that were collected. And you can see very clearly that south of 200 East, we're actually not seeing those higher velocity sediments where that basalt, we're not seeing basalt south of the roadway here. We see that the reflections and the refractions, the color scales actually match up pretty well. And we have a very deep sequence of the Hanford Formation, or the reds, the lower velocity sediments closer to the road, and it's actually thinning out as we move further south. And the Ringgold formations, or those sort of intermediate colors, are thickening as we move further south. We were hoping within this area to have some indication or seeing some sort of incision. The conceptual site model of a paleochannel or transmissive zone is sort of this dipping feature, but we're not actually seeing that within the seismic data here, the seismic interpretation. We also collected ERT data. This was in 2 separate field campaigns. So area 3 has really large electrode spacing, 25 meters, and this was done as a series of different ERT surveys. And then this up here, East-West 1, North-South 1, and North-South 2. That was collected in a separate field campaign where we had 10-meter spacing. And if you look at the Area 3 profile, it's sort of interesting to see the contrast in that blue area. There might be textural contrast or changes in moisture content, and sort of how that's shown is very similar to what we see along the east-west line in that shallow area. You can see that blue zone. Within Area 3, very deeper, we also see a very large electrical contrast. It has some undulations within it. And I actually don't have time to show this here, but it actually matched what we're seeing in the GFM in the shallow area quite well. But interestingly, along the North-South 1 and North-South 2 profile, in the shallow area, it matches what we see in the seismic profiles, but we do see a higher conductivity area deeper. And these conductivities are not indicative of metallic infrastructure. There's no known waste sites here. So we're still trying to figure out why we're seeing these higher bulk electrical conductivities along that North-South 1 and North-South 2 profile. But we're actually not seeing anything that would be indicative of sort of the conceptual paleochannel model. Oh, I was going to show you a close-up, but I already talked about it. Finally, Delphine and Chris are working on visualization of geophysical data in Socrates. So Socrates is the suite of comprehensive rapid analysis tools for environmental sites. It's a web application for environmental data access, advanced visualization, and rapid data analytics to support environmental decision-making on remedy decisions, optimization, exit strategies, and monitoring. So the Socrates suite is comprised of 7 modules, including Origin, which is shown here, which is the 3D visualization of subsurface geology wells and data. And they're working on incorporating ERT within Origin. They've prototyped several ERT field campaigns. So here, the ERT images is actually shown as a point cloud. Because the ERT is solved through finite element modeling, this is sort of the data in one voxel within that finite element mesh. But this gives a really powerful way to sort of view the data next to one another and just see how they compare to one another. And understanding the uncertainties within all of these different data sets can really help us come to a better interpretation looking at it together. So in summary, surface geophysical methods are helping to provide stratigraphic information on the Hanford site. It's providing a first-line evidence, and we're hoping that it can help support decisions about locations and the need for new subsurface characterization wells. I showed in some areas that, especially in the shallow areas, that ERT and seismic might potentially be providing a better spatial understanding of lateral transitions in the shallow area. Along that one profile, that seismic profile, the ground truthing through well observations helped tremendously to guide the interpretation. We still have work to do to understand the relationship between geophysical and properties and hydraulic properties, and the visualization of geophysical data is ongoing in Socrates. So with that, thank you, and I look forward to your questions and discussion.
Great, thanks, Judy. I think we'll do 1 or 2 quick questions from the chat, and then I will pass this over to Nick Chifoku to moderate a discussion. Judy, there was a question in the chat about, and it was actually directed to Mike, so we'll let Mike answer too, but it related to whether geophysics can replace the CSM. If we have ERT everywhere, is there a chance that geophysics can replace the knowledge of the geologic framework? So I'd like you to respond to that question if you could.
Sure. No, geophysics can be used as another tool on a site to help define the conceptual site model. It's not meant to be a replacement. Geophysical techniques they provide you with geophysical properties, but they do need to be related to, you know, lithology and physical properties. So we always need ground truthing of geophysical data, and it's certainly not meant to be a replacement of, you know, to formulate the CSM.
I'd like to comment on that too. So in just in general, you know, the subsurface is always more complicated than we think. And so CSMs, I believe, should always focus on bringing in multiple lines of evidence. Like, for instance, when Mike showed that, when Mike showed the when Mike showed the example of Silicon Valley, those weren't the final cross sections just using geology. He had initial interpretations that helped build and better understand the hydrogeology data, the groundwater chemistry data. But then a lot of that chemistry data, groundwater data, also helped drive the geologic interpretation. So you always need to bring as much of the data that you have available. And so for instance, I wouldn't want to not do a geologic interpretation just because I have other data sets that are, you know, giving me some indication of the subsurface.
Great. Thanks, Rick, and thanks, Judy. There was also a question in the chat a little bit earlier about the use of these kind of deterministic interpretations of the subsurface. And what opportunities are there with geophysics or with sequence stratigraphy to try to incorporate uncertainty into the interpretation? So if you only have one subsurface model, is there a way to extend that probabilistically or in some way, you know, account for the uncertainty in the models that we're coming up with? So I think I'll bounce that over to Mike first, and then we can come back to Judy to answer with regards to geophysics.
Sure, thanks. Good, yeah. Oops, we have a echo. Okay. Yeah, thanks. We should always carry multiple working hypotheses forward. It's the subsurface, and the more lines of it all has to fit together, you know. So yeah, we should certainly expect that new data will improve our conceptualization of the subsurface. So we always carry forward multiple working hypotheses, and there's no truth like tracer truth. So you know, in terms of which bits of evidence we you know, we can hang our hats on, you know, the contaminant chemistry or tracers are clearly superior, but that's not always available. So I think the answer is to carry forward multiple working hypotheses that you know, there is a such thing as a poor interpretation of the subsurface. I won't sugarcoat that, but there are in some cases equiprobable interpretations of the subsurface, and that's what we you know, that's when we need to collect additional data, or maybe we don't if both answers are acceptable given the problem at hand.
Great, thanks, Mike. Judy, can you comment on that, the issue of uncertainty?
Certainly, you know, modelers.
Judy, you're on mute, I believe. Oh, no, I'm on mute. Sorry, you're good. No, you're good.
Certainly, modelers understand the uncertainties associated with their models. It's hard to convey that sometimes to other people. You know, there are deterministic ways to invert your geophysical data. You can also use a Bayesian framework, which has uncertainty built in. Newer machine learning models are rapidly being explored, which also incorporate uncertainty. And I think that there's going to be much more of the machine learning in geophysical interpretation as we move forward.
thanks. There's also a question in the chat directed to Judy about 2D and 3D ERT having been used at Hanford for several decades. So the question is how the ERT surveys can help build evidence of contaminations to DOE. I think the question is perhaps aimed at what more is there to do with ERT? Where are the advances to be made? Where do you see research with ERT going?
Yeah, I mean, I think I commented on some of that with the newer machine learning to sort of incorporate uncertainty. You're right, ERT has been used quite a bit on the Hanford site. There's also been a lot of application of time-lapse ERT to look at remedial applications. Tim Johnson has a wealth of work on that. There's a lot more uncertainty, I would say, in looking at characterization images because it has multiple dependencies. So it's going to be important to look at these new opportunities to help interpret the ERT data as we move forward. And also most of the wells on the Hanford site are steel cased. So, you know, in seismic, we can do a vertical seismic profile and sort of hopefully, you know, ground truth, which is what you saw in James's work. And it would be really helpful to be able to do that with ERT as well, to just get a sense of what the bulk electrical conductivity is associated with a particular stratigraphic unit.
Great, thank you. There was a comment in the chat about geophysics and ESS being complementary and ESS being built on all different types of information feeding into it along with the geologic principles. So perhaps Mike or Rick or both of you, if you could comment on where surface geophysics fits in. There was use of borehole geophysics in the ESS part, but could you comment on where surface geophysics fits in, either for groundwater or even for petroleum applications, which you're both familiar with?
Yeah, sure.
Rick, you're muted. We don't hear you.
The petroleum industry, and what you find there is you don't geophysics and a strong geologic model are always married in the petroleum industry. I mean, like classic sequence stratigraphy, and that was born out of using geophysical data, seismic stratigraphy data. So when I came into back in the 80s and into environmental, and then even to this date, I haven't seen that happen, and I think that's an important improvement that we and opportunity in our industry is to marry them and come up with some more improved interpretations of the subject.
I can add on to that a little bit. I've interpreted a lot of 2D and 3D seismic reflection data for exploration purposes and for groundwater purposes as well. And they're absolutely complementary. And I think that what Rick said is, in terms of the opportunity, is that there's far too many monitoring wells out there, period. Most of them are not informing, not giving us the information that we need, and they're redundant in a lot of cases, and they're a waste of money, frankly, the sampling and analysis of them. So we fully intend to leverage geophysics, airborne, surface-based, to the extent that we can to make better upfront decisions and really improve the efficiency of monitoring and remediation programs.
I'll just add to that and I mentioned this during the presentation.
Did you have a? Oh, sorry. Go ahead.
Yeah. That geophysics can, we're hoping it can help provide where those gaps are, where it would be most efficient to install a new well. I think that's a pretty good use of using geophysics to find where that well should be, to Mike's point. Yeah.
Nick is monitoring the chat for additional questions. Nick, do you see any there?
Yes, I do. Another question for you, Judy. Can you hear me okay? I hope so.
I do.
The question is that, have you tried joint inversion of electrical resistivity and seismic data to guide the imaging and interpretation process? I thought this was a very good question. So go ahead, Judy, please.
Yes, actually, James worked on that, I guess, last fiscal year. He looked at using a particular framework to do the joint inversion. It didn't work particularly well, but that's not to say that we won't look for other opportunities to jointly interpret the data by doing a joint inversion. But our first attempt, it didn't work very well.
All right. Well, thank you very much. I think this was a great seminar. We are almost on time to some closing remarks. Thanks again to Mike, Rick, and Judy for their excellent presentations today. We are very happy to have Mike, Rick, and the other members of the team here with us today. Yesterday, actually, as a matter of fact, and today here at PNNL. Well, thank you very much for everyone that actually joined today in this seminar. As you exit this meeting, you will be asked to complete a survey, and thanks in advance for providing some feedback to us. This is greatly appreciated. And the last announcement that I will make today is that we are going to have a seminar in August, and we will determine the specific date and speakers pretty soon, but the seminar will be around developing sustainable site end states for remediation projects. And we really want everyone to actually join us in the future seminars, and especially in the seminar that will be in August. Well, thanks again. Thanks again, Judy. Thanks, Mike, and thanks, Rick. And enjoy the rest of the day. And Karen is here. If you have anything else, Karen, please go ahead.
Nope, you covered it, Nick. Thank you very much. And thank you to our speakers and all our participants.
Have a great day, everyone.
Bye-bye.
Thanks for your time.